Hello everyone, this is Chun-Wei Huang from Minchi University of Technology. Today I'm gonna give a talk about an exploratory study of mapping breeding bird richness using a deep learning technology. Before I get started, I would like to thank for the financial support from Ministry of Science and Technology Taiwan. This is my outline. Global urbanization is one of the major drivers which lead to biodiversity loss. This figure shows how fast the world urban population grows. It took all of history until 1960 for world urban population to reach 1 billion, but only additional 26 years to reach 2 billion. It's really incredible. After 2007, there are more than half of people live in cities. The rapid global urbanization significantly drives land use and land cover change. To build up a tool for monitoring impact of urban-driven land use land cover changes on biodiversity, it's important to understand the relationship between landscape patterns and species. Previous landscape ecological studies have indicated that different landscape structures may affect the movement of different species, nutrients, energy, and matter. This figure with many micro-landscapes tells a story about how different habitat abundance and the fragmentation affect anthropod communities. However, so far the challenge of building up a model to monitor the impact remains due to data scarcity on landscape patterns and the species distribution. Neil Jeans and other researchers from Stanford have applied a deep learning neural network to capture the special features of different landscapes using satellite imageries. These feature maps show the capability of their deep learning technology in recognizing the patterns of urban, suburban, rivers with homogeneous forests and roads. Their deep learning neural network then built up the relationship between the landscapes with socio-economic status, such as income for countries which have scarce socio-economic census survey in Africa. As such, their deep learning neural network show the potential to capture the features of different landscape structures in images for other geospatial big data analysis. So our research goal is to incorporate a deep learning neural network with Landsat satellite images to explore the relationship between ambient richness of breeding birds and the landscape patterns along urban-rural gradients in Taiwan. To find a better deep learning neural network, we also did the sensitivity analysis for hyperparameters such as kernel sizes or extents of input satellite images. In this study, we used a citizen science-based database termed BBS Taiwan for bird biodiversity data. So far, they have collected data for over 10 years and 480 sites. Because we would like to analyze the impact of urbanization on birds' biodiversity, we compile data in sites under 100 meters above mean sea level. So we got the 943 data pairs, which means satellite image with corresponding bird richness in total for training the model. For input of the deep learning neural networks, we use Landsat A satellite imageries from 2013 to 2019 with 30 meters for resolutions. As I mentioned, we also did the sensitivity analysis for different extents here. For the output of the deep learning neural networks, So far, we arbitrarily classify biodiversity data into three categories, including low, medium, and high, based on the BBS Taiwan data using the Jenks Nature Breaks classification method. So this is the model structure of our convolutional-based deep learning neural network. We did sensitivity analysis not only for the extent of landscape for representing ambient richness at the community level, but also the kernel sizes used to capture the special characteristics of the landscapes. Overall, we have to fine-tune over 50,000 trainable parameters. And this is the results. And so far, I have to say our results are not good enough for all the models. The accuracy of the deep learning neural networks are averagely under 70%. Before we go further analysis for model performance, I would like to introduce two indexes commonly used for evaluating performance of machine learning models, precision and recall. Precision is the ratio of true positives to true positives plus false positives, which means among all of the predicted positives, how many true positives can be identified. On the other hand, recall is a ratio of true positives to true positives plus false negatives, which means how many actual positives can be found out using this model. If we go deeper to check the precision and recall for the models, we can find better precision to classify high biodiversities by model using 4 kilometer square input satellite images here. Similar situation resulted from the model using convolutional kernels with 16 pixels in area. However, their recalls are not as good as their precision. But for the model using kernel size with 36 pixels in area, we cannot find any better results compared with previous ones. So we used the deep learning neural network with 4 pixels for the convolutional kernels and 4 kilometers square for the extent of input satellite images to predict all the area under 100 meters above mean sea level in Taiwan. This is the results. Once we can have better results of the deep learning neural networks, we can use them to estimate and monitor the change of land use land cover change and the corresponding change of avian richness. And this is prediction for 2016. And this is the prediction results for 2019. Here we're gonna give a brief discussion of the challenges to improve our model. The first one is about training data scarcity. As we can see, the first two studies in this table show that successful deep learning neural networks relied on numerous training data. Different from the conventional machine learning models, deep learning implies more hidden layers which introduce numerous parameters to be trained and fine-tuned. As such, increasing training dataset is the first task to improve our model. The second task is to find a better or suitable deep learning model for this experiment. So far, we only used the 4 layers convolutional neural networks, the NAT, for exploring the potential. we definitely need to improve by compare different deep learning models. So now we are putting efforts in several works to overcome the two challenges mentioned in the last slide. The first one is now we are using point survey data set from BBS Taiwan instead of site data set. In so doing, we can increase the numbers of training data pairs to 3,900. So far, we got only 943 data pairs. The second idea is to improve our model is improving output classifications using transfer learning based on landscape ecology. For example, Benedict in 2015 did a meta-analysis for 75 cities and pointed out that the class area and the connectivity of green spaces are the most important driving factors on urban biodiversity. Based on his results, we can analyze the landscape matrix even for areas without bird survey data. In so doing, we can increase training data set by transfer learning from landscape structure to avian richness. The final idea we are doing now is using semantic segmentation-based deep learning neural network. Actually, we are using UNet to provide dense labels in a patch of input images. In so doing, we can map landscape structures within a buffer area for each pixel in the input image, so that we can assist transfer learning from landscape structure to urban biodiversity. We believe that deep learning technology has potential to automatically monitor the change of bird richness based on the land use land cover changes. Hopefully, we can successfully build up a monitor tool for urban planners so that they can build up an eco-friendly landscape. This is our reference, and thank you for your listening.